All right, so today we'll talk about finding concurrency bugs before production does. I'm going to show you FizzBee, a tool that explores every possible execution of your system to find race conditions. Testing concurrent or distributed systems is hard. You can have two API requests that hit your service at the exact same microsecond and under very specific state conditions. FizzBee is a tool that finds bugs by exploring every possible execution. Instead of random testing, it does exhaustive verification. Quick note, you should read the code while listening. Hit pause if you need to. Here's a typical race condition scenario. Two customers trying to buy the last item in stock. Now, the way this code is written, it's very possible that we end up with a negative stock amount. While this is a contrived example, it's a common concurrency scenario that traditional testing approaches typically don't catch. FizzBee can make you aware of it before it happens in production. To use FizzBee, you can install it with pip, the Python package manager. Alternatively, you can use the web playground with no installation needed. We can model that inventory bug and see how FizzBee can help us find it. Here's that inventory system in FizzBee. We'll start with one item in stock. The purchase action models customers trying to buy. The key here is that FizzBee will run multiple purchase actions concurrently, just like in production. The assertion at the bottom says that the stock amount should never go negative. This is what we call a safety property, something that must always be true. When designing your system, you should strive to differentiate between fairy tales and reality. You should think about the serial versus the atomic behavior of your system. Now, specifically, atomic actions are like transactions. Everything succeeds or nothing does. And so database people love atomic actions. On the other hand, with serial actions, basically serial actions model the real world in the sense that they capture the fact that things can fail halfway through. And there are cases, for example, with banking, where things failing halfway through can lead to money vanishing as a result. Now, in FizzBee, serial is the default. And I think that's because production is, more often than not, production is just not atomic. An important concept of FizzBee is that actions only run when their guards are satisfied. Now, looking at the wait for enable action, it has a guard, and that is the if enabled predicate. This action, the wait for enable action, cannot run until the enabled state variable becomes true. On the other hand, the enable action at the bottom, it has no guard, so it's always enabled, which means that it can run anytime. So in FizzBee, at each step, right, it's going to look at all actions. It's going to check the ones which are enabled, and it's going to try those. And this is how FizzBee explores your state space. In FizzBee, any keyword models non-determinism, which means that we can model unknown outcomes. Now, if we take the example of a network request, we can have a request that succeeds, errors, or times out. Now, with FizzBee, we can systematically explore all those possibilities and basically do an exhaustive exploration and not just random testing. Functions in FizzBee are pure computations. They have no side effects and they can modify state. Now, looking at the can afford function, it checks if an account can afford a withdrawal, and it does so with respect to its current balance and the allowed minimum balance. The function, the can afford function, doesn't change the account balance. It only computes a predicate value. With functions, you want to use them for complex logic, guard conditions, and really anything that you want to compute without side effects. And so when it comes to the difference between functions and actions, functions are meant to be pure computation, and your actions should focus on state changes. Semantically, safety properties are invariants, things that must never be violated. Some examples of invariants will be checking that there are no negative balances, or that we want to check that in a consensus protocol like Raft or view stamp replication, that we only have one leader at any given moment. So these kinds of conditions or assertions, they are checked in every single reachable state. If FizzBee can find any sequence of actions that violates these assertions or these invariants, it will show you exactly how. Liveness properties can be a little tricky to understand at first, but it's important to understand them. FizzBee handles liveness properties using three kinds of predicates: the eventually predicate, the eventually always predicate, and finally the always eventually predicate. So let's go through each one of them. So with the first one, we use the eventually predicate when we want to ensure that a condition eventually becomes true. So for example, we can check if some system eventually starts up or if a queue eventually empties. With the second kind of predicate, the eventually always predicate, we want to ensure that a condition not only becomes true, but that it stays true. For example, we can check if a system eventually becomes stable or if a scheduler eventually schedules a job. Lastly, talking about the always eventually predicate, we use that one when we want to ensure that a condition repeatedly becomes true. An example for this would be to say that we want to check if a queue keeps draining or if a scheduler keeps scheduling jobs. So when it comes to those three kinds of predicates, right, again, it's eventually, eventually always, and always eventually, right? It's important to decide which one to use depending on your needs, the needs of your system. To further illustrate the different kinds of liveness properties, we can look at this code that models a queue that processes items. We use the queueEmpty predicate to check if the queue will empty at least once. This is a good liveness property to ensure that the queue does start up. And then we also use the keeps draining predicate to check if the queue will repeatedly empty even if items keep arriving. This is a good liveness property to ensure that the queue keeps draining. It is important to choose the right liveness property for what you are verifying. FizzBee uses the concept of roles to model different actors in your system. This lends well to the dynamic nature of distributed systems, where we often use the terms producers and consumers, or clients and servers. Now, each role is like a separate thread of execution. These threads, we can conceive them as running concurrently, interleaving in all possible ways. The repeat keyword controls how many times the role's actions execute. This models real behavior patterns. There are two key patterns with the repeat keyword. There is repeat n and repeat forever. In the case of repeat n, we want the role's actions to run exactly n times. An example for this would be a client making 3 requests. For repeat forever, what we want is to have the role's actions, we want them to run indefinitely. And again, a good example for this would be a server processing requests. The yield points are where other roles can interleave, and this models concurrency behavior in your system. Here's a classic concurrent pattern. Producer adds to queue, consumer removes. The producer role runs 10 times, the consumer role runs forever, and the queue size, or the queue has a max size. The assertion at the bottom verifies the queue never overflows. FizzBee checks this across all possible interleavings of producer and consumer. FizzBee handles branching logic using the oneof keyword. Oneof models non-deterministic choice. A request might succeed, timeout, or error. Not all three, just one. This is different from the any keyword, which picks values. Oneof, right? The oneof keyword picks execution paths. FizzBee uses the parallel keyword to model parallel execution. This means that all statements inside the parallel block execute at the same time, but in any order. For example, we can model a database write, cache invalidation, and audit log as a parallel block. They all happen, but the order varies. This is really useful to uncover possible race conditions between operations. The await keyword models synchronization between actors. It blocks the current role's execution until a condition becomes true. So in this example, workers wait for a leader to be elected before sending requests. The await statement blocks the worker role until leader elected becomes true. This is how you model coordination in distributed systems. One part waits for another to reach a certain state. Sometimes you need to verify fairness and the idea that everyone gets served and there's no starvation. The first assertion checks that everyone eventually gets at least one request processed. The second assertion is stronger. It ensures that everyone keeps getting a fair share. And so we end up having a situation where at least half of the requests are processed. Together, such fairness properties ensure that your system doesn't accidentally starve certain clients. Real distributed systems need to handle node failures gracefully. This example models leader election where nodes can crash at any time. Now, looking at the node fails action, it's a serial action and not atomic. The node marks itself as not alive, but well, we need to ask ourselves, what if it crashes before releasing leadership? We can basically end up with a zombie leader, right? And that's a dead node that others still think is the leader. The liveness property at the bottom uses eventually always to verify that we always have a leader among the living nodes, or that all nodes have failed. This pattern, right? This pattern finds critical gaps in failure handling, the edge cases that cause split branch scenarios, and coordination failures in production. Here is a model of a token bucket rate limiter with replenishment, and we have two roles running concurrently. Request handler consumes tokens and token bucket replenishes them. The properties verify tokens stay in bounds and eventually become available, so no permanent throttling. When FizzBee finds a bug, you get a complete trace, every step to reproduce. FizzBee will yield a specific sequence that you can use to reproduce the bug. You can even use it to write test cases. The information from the trace can be very useful for debugging. In the case of protocol design, FizzBee can really help you sleep better at night. Debugging FizzBee models is all about visibility. So let's look at three key techniques. First, you want to track state evolution, and the way to do that is by the use of typical print statements. You want to put that before and after each action to see exactly how state changes. This helps you understand the execution flow. Second, when you notice that an action isn't firing, what you typically want to do is print your guard conditions. FizzBee will show you exactly why the guards aren't satisfied. This takes the guessing, or it removes the amount of guessing you have to do to understand why something isn't happening. And third, you want to use assertions as tracing tools. You should create assertions that always return true, but print when interesting states are reached. This will let you trace specific scenarios without failing the model. Remember, FizzBee is deterministic. The same model produces the same results. So use print statements liberally to understand what's happening in your model. Here are 3 fundamental patterns you'll use in almost every FizzBee model. The first pattern can be referred to as the at most one pattern. It represents mutual exclusion. It is useful when you need to ensure conditions such as having only one leader, only one process in the critical section, or only one owner of a resource. You want to use this pattern to surface split brain or race conditions. The second pattern can be referred to as the progress guarantee problem pattern. It ensures that your system doesn't get stuck. You typically use it to ensure that something happens at least once, or you want to check that something happens repeatedly. It's the pattern that forces you to really think about deadlock freedom in your system. Now, the third pattern can be referred to as the conservation laws pattern. It verifies nothing gets lost or duplicated. It is useful when you want to ensure that messages don't just vanish or that resources don't appear from nowhere. You don't want money to just disappear, or that some control or aggregate variables, they always add up to some amount. Together, these 3 patterns cover about 80% of what you'll need to verify distributed systems. Here's your introductory cheat sheet for FizzBee. It covers the basic structure, properties, and control flow. Print this, keep it handy, reference it while modeling. Everything you need to know to get started is here. Get started with FizzBee. Don't attempt to model your entire system. Instead, pick one tricky component, then model its basic operations. Once you've done that, you can start thinking about and implementing its safety properties. And from there, you can work on implementing and checking Liveness properties as well. Remember, the goal is to start finding bugs before production does. So that's FizzBee, formal methods without the math degree. If you found this helpful, hit like and subscribe for more technical content. You can drop a comment about what you're planning to model. And thanks for watching, and I'll see you in the next one.